Hello, my name is Deborah Ramnath, and I'm here to present research conducted at the University of the West Indies, Trinidad and Tobago. Today's presentation is entitled Z Factors for Carbon Dioxide with Hydrocarbon Gas Impurity. The sequestration of CO2 in depleted gas reservoirs is a practical form of reducing atmospheric CO2 emissions. This is illustrated in the figure to the right, where CO2 will be captured from the atmosphere and injected underground for storage, such as within depleted gas reservoirs. An important question then becomes, what volumes of CO2 can be safely stored together with the residual natural gas present in these reservoirs? An important parameter required for the calculation of gas volume is Z factor. In this study, we will be testing the applicability of the correlation presented in 1993 by Piper, McCain and Corridor for determining the Z factor for CO2 natural gas mixtures by treating natural gas and other pure hydrocarbon gases as impurities of CO2. The mixtures investigated in this study is similar to those that will be encountered during CO2 storage within depleted gas reservoirs. Let us then understand what Z factor is. Z factor is also known as the gas compressibility factor or gas deviation factor. It is a correction factor which describes the deviation of a real gas from ideal gas behavior. In a graph of Z factor versus pressure, for an ideal gas for all pressure conditions, C will be equal to 1. This is illustrated by the horizontal line, which represents perfectly ideal gas behavior. However, in the case of real gases, a completely different trend is observed. Firstly, at atmospheric pressure, Z is equal to 1. As pressure increases at the lower pressures, attractive forces dominate, which cause Z to be less than 1. As pressures continue to increase, at a certain point, both attractive and repulsive forces are negligible and Z will return to 1. At higher pressures, repulsive forces dominate, causing Z to be larger than 1. This gives the characteristic curve as seen here. Z factor is an important parameter required for calculation of reservoir gas in place volume. In the context of carbon storage, accurate determination of Z factor is important in estimating the volume of CO2 that can be sequestered, as well as to monitor leakage of CO2 sequestration within depleted gas reservoirs. This is done through an adaptation of the commonly used P over Z plot, which is traditionally used in the oil and gas industry. The figure to the right is an illustration of this concept. Firstly, a linear line is observed from the extrapolation of the historical production of gas from a hydrocarbon reservoir. This is labeled as natural gas part. A second parallel line can be drawn which reflects the predicted performance of the same reservoir with CO2 instead of hydrocarbon. And this is seen as the analogous CO2 reservoir part. As it can be observed, the CO2 reservoir part line is higher than that of the natural gas line. This is because at same pressure and temperature conditions, Z factor values of CO2 are lower than Z factor values for pure hydrocarbon gas. The P over Z linear equation used to generate this graph was presented by Lau and Fraley in 2004 and is as seen here. In order to use this equation, Z factor of the produced hydrocarbon CO2 mixture, as well as the Z factor of the residual hydrocarbon CO2 mixture and Z of injected CO2 mixtures are unknowns and must be determined. Z factor of injected CO2 is that of pure CO2 and is well established and can be found in published literature. This study would seek to identify a suitable method to determine Z factors of residual hydrocarbon CO2 mixtures in depleted gas reservoir. How then can we determine Z factor? One such method to determine Z factor is that of experimental measurement. This gives the highest accuracy among methods. However, it is expensive, time-consuming, and would only be applicable for the pressure and temperature ranges that are being investigated. As such, in the upstream gas industry, reservoir engineers commonly use Z factors for natural gas from well-known charts and correlations. An example of this chart is that of Standing and Katz in 1942, which is seen to the right, where pseudo-reduced pressure as well as pseudo-reduced temperature are used to determine the Z factor. This chart is used for hydrocarbon gas. In order to account for the presence of CO2 and other non-hydrocarbon gases in natural gas, additional correlations must be used. Such additional correlations will be those that were developed by Wichert and Aziz in 1972, as well as Kabushi Burroughs in 1954. After reviewing these correlations and charts, a more accurate method for predicting Z factor for natural gas containing as much as 70% of these impure gases was developed by Piper, McCain and Corridor in 1993. Here we see the correlation that was developed by Piper and others. In their equation, CO2 gas and other non-hydrocarbon gases that will be present in natural gas are already included into their equation, which eliminates the need for involving additional correlation. To use this correlation, the gas composition of the gas is needed. If not available, the specific gravity of the gas can be used. This correlation uses alpha and beta coefficients to determine, and alpha beta coefficients are as shown to the right, and these are used to determine the functions J and K. Once the functions J and K are determined, we can then find the pseudocritical pressure and pseudocritical temperature, which are used to find the Z factor for a mixture of hydrocarbon and CO2, or for pure hydrocarbon gas. In this study, Z factors were determined using the developed correlation by Piper and others for 6 mixtures. The composition of the mixtures are shown on this chart to the right. Mixtures 1 and 2 contain a mixture of carbon dioxide and methane, while mixtures 3 to 5 is a mixture of carbon dioxide as well as a dry gas composition from a natural gas reservoir. And mixture 6 is that of the pure dry gas, which would have been obtained from a natural gas reservoir. Mixtures 1 and 2 were investigated at a temperature range of 160 to 400 degrees Fahrenheit and pressure range at 200 to 10,000 psi, while mixtures 3 to 6 at the pressures of 160 and 220 degrees Fahrenheit and a pressure range of 200 to 5,000 psi. Once Z values were computed for these mixtures, they were then compared to Z factors from published experimental results. Now we'll begin at looking at the results for the first mixture, which contained 80% CO2 and 20% methane. From this chart, we see the various temperatures that were investigated as well as pressures. It shows the percentage difference between the predicted, which would have been calculated from this study, and experimental Z factors from published data. From analysis of the percentage difference, we see less than 5% difference obtained for pressure range of 220 to 400 degrees Fahrenheit for all the pressure ranges investigated. A look at 160 degrees Fahrenheit, higher percentage difference was obtained, and they were all under 10%. The average absolute percentage difference for each temperature was also calculated as seen in the last row, and they were all under 5%. Moving on to mixture 2, which contains 60% CO2 and 40% methane. Again, a similar chart as before is seen. An analysis of these results showed less than 5% percentage difference for all the temperature and pressure ranges investigated, and less than 2% for the average absolute percentage difference as shown in the last row. Here we see graphs for each of the temperatures investigated for mixtures 1 and 2 of Z factor versus pressure. The solid lines represent calculated values, while dashed lines represent experimental values. From these lines, we can see that similar trends are observed for both calculated and experimental values. In our previous mixture, we looked at carbon dioxide and methane. We'll now be looking at a mixture of carbon dioxide and dry gas taken from a natural gas reservoir for mixtures 3 to 5, and mixture 6 will be that of the pure dry gas. Here we see mixture 3 to 6 and the various pressures investigated at a temperature of 160 degrees Fahrenheit. From analysis of the results, we see that less than 10% percentage difference was observed, and average absolute percentage difference ranged between 0.89% to 5.58%. Again, we looked at same mixtures, but now at a higher temperature of 220 degrees Fahrenheit. Percentage difference of less than 5% was observed for all mixtures, and average absolute percentage difference of less than 4% was obtained. Similarly to before, plots of Z factor versus pressure for calculated and experimental results were conducted, and similar trends were seen. In conclusion, the Z factor for CO2 natural gas mixtures were investigated by treating natural gas and other hydrocarbon gas as impurities in CO2. The investigated correlation by Piper and others was determined to accurately predict Z factor for a range of pressure and temperature conditions and mixtures containing 0 to 80% CO2 and 100 to 20% hydrocarbon gas. The pressure, temperature, and gas compositions that were investigated in the study will be representative to those that are encountered during CO2 storage within depleted gas reservoirs. Results from these studies showed between predicted and published experimental Z factors of average absolute percentage difference of less than 5%, a percentage difference of less than 10% at 60 degrees Fahrenheit, and less than 5% at 220 to 400 degrees Fahrenheit for all pressures investigated. In conclusion, the results suggest that the tested correlation can be suitably applied to determine Z factors, which are required for use in estimation of CO2 sequestration volumes and to monitor CO2 injection. This brings me to the end of my presentation. I would like to say a special thank you to my colleagues at the University of the West Indies, Professor Rafi Hussain. Thank you.